Thanks very much, Jim, and thanks very much for inviting me to come here. It's a great pleasure. The talk isn't going to be terribly scientific, all right, so I'm just going to give you a personal perspective of landing on a comet, apart from I didn't personally land on the comet. And I will say we a lot. We did this, we did that, we did the other. You know, I didn't do anything. I am a science advisor to the Ptolemy team, and Ptolemy is one of the instruments on Philae. But, you know, when I say we, you know, we engineers, we technologists, we rocket scientists, we built this mission, you know, get a bit carried away. So, just first of all, a bit of revision as to why we would actually want to do this. It's all part of a sort of program of building habitable worlds, of trying to understand where habitable worlds come from. Now, of course, we know that for life on habitable worlds, we need water and carbon. And when the Earth first got going, it was incandescently hot. Its atmosphere was in effect steam, and gradually cooled down. This is Kilauea. And solidified. Now, during this period, it was kept incandescently hot, molten surface by bombardment by asteroids and comets. Gradually, that bombardment died down and the surface solidified. But bombardment continued, but at a much, much lower rate. And the asteroids and comets then started adding volatiles to the planets rather than removing them. So what we've got now on Earth is a mixture of indigenous water and carbon. So the stuff that was there from the protoplanetary disk 4,567 million years ago, and exogenous from asteroids and comets. Now you might say, well, hang on a minute, the asteroids and comets are made from the same stuff that the protoplanetary disk was made from. You know, they were made from the same protoplanetary disk. But the Earth went through a lot of fractionation. The water was fractionated, carbon was fractionated, isotopically fractionated, and a lot of the material in these asteroids and comets hasn't been. So what we want to try and see is how much was added at a later stage. Because what that does is that speaks to what has happened on other planets, because Mars, Mercury, Venus, the satellites of the outer planets, they also were bombarded by asteroids and comets. They also will have these volatiles added to them. And of course, it also means a lot for looking at other planetary systems to try and understand what's been going on in other planetary systems in terms of what volatiles might be present on other planets and moons around some of the gas giants that have been observed. So this is one of the reasons why we want to do it, okay? Again, a bit more revision. Asteroids and comets orbit the sun. They're relatively unprocessed remnants. Asteroids orbit between Mars and Jupiter on circular, you know, roughly circular orbits in the plane of the ecliptic, and they're mainly made of rock and metal. Comets, of course, are much more interesting and exciting in terms of their dynamics because they've come from either the Kuiper belt or the Oort cloud. The Kuiper belt we know a lot about, you know, its most famous occupant is probably Pluto. The Oort cloud, we don't know, we've never seen it, it's a hypothetical construct, but it has to be there. Some comets are on very, very highly elliptical orbits, not necessarily in the plane of the ecliptic, and importantly, they haven't been differentiated. So some asteroids have got very, very hot, differentiated, got a metal core, like the Earth has. Comets haven't, they're mainly dust and ice, and in that dust there is a lot of carbon. So we've got a great history of cometary missions in Europe, in terms of our past. The first cometary mission was in 1985-86 to Halley's Comet. The first spacecraft to get there were Vega 1 and Vega 2, which are Russian spacecraft. They were, I can't remember whether they were on their way to or on their way from Venus, but they were sort of, you know, moved a little bit, and so they flew past Halley, and the spectrometers on board took the first compositional data of a cometary nucleus and showed that it was very, very highly dominated by carbon, hydrogen, oxygen and nitrogen. And that was very interesting because up until then, the assumption had been that comets were icy snowballs, dirty snowballs, sorry. The view that had been proposed by Whipple. So Giotto was 3 days after Halley. So these were Russian, this was the European Space Agency mission. And this took a close-up image of a cometary nucleus. It flew by about 600 kilometers from the nucleus. And so we got this, the very first close-up image of a comet. And you've got this sort of almost ovoid object with a very big jet at the top. The next cometary mission was in 2006, and this is a NASA mission to Comet Wild 2, the Stardust mission, and this flew through the coma and brought material back. It had a very strange collector, which was a bit like a tennis racket, and in the squares between the strings was a material called aerogel. So this sort of tennis racket was out on the side, or it unfolded itself and came out as it swept through the coma and collected a lot of cometary dust. The problem is, aerogel, which is what the collecting mechanism is, aerogel is a really, really low density solid. I mean, it's got a density of about 0, so very, very low density. And the idea was that the grains would embed themselves in the aerogel and that it would be very easy to pick them out. Well, it wasn't. A lot of the grains actually exploded and made very strange tracks in the aerogel, and it was difficult to pick them out. What we got is a lot of information about the silicates in the comets, but nothing or very, very little useful about any carbon that's in there. And of course, nothing about the ice and about the volatiles. So now we have this mission, Rosetta. First results are percolating through, which is really great. So this is a European Space Agency mission, and it's been a long time in the planning. Now, I'm not going to show this. Has anybody seen this video? Some people have, some people haven't. It's really worth watching. It's about 5 or 6 minutes long. And this is the European Space Agency showing that when it pulls its finger out, it can do public engagement really, really well. This guy here, that's Aidan Gillen, who is Peter Baelish or Littlefinger in Game of Thrones. Okay. One of the few people who didn't stick a dagger into Jon's... Oh, spoiler, sorry. So he was in this. In this movie, and it is for the public, and it's talking about, you know, how is a comet built and why is it important to actually study it. And it's a great resource if you're going and talking to people, especially schools, about comets. And it's a real Hollywood blockbuster type thing. It's set to really, really stirring music, which makes you proud to be European. It's just really amazing. Okay, so where were we? Right, so Rosetta, the mission, and here I show you, you know, the road show, which is on the back of this. On the back of the T-shirt. Come back. So it was launched in 2004. It had all these gravity assists: 1, 2, 3 gravity assists from Earth, a gravity assist from Mars. It flew by 2 asteroids, asteroid Stynes and asteroid Lutetia, and that lot took 8 years. Okay, so it was building up enough sort of momentum to help it catch up with the comet. Then it went into hibernation for about 18 months, not quite 2 years, and in January 2014 it woke up. And so it was switched on again. So here's this thing that was, you know, millions and millions of kilometers away, and it's been asleep in the deep cold of outer space. It's been asleep for 2 years. Switch it on. Is it going to work first time? Well, I've been saying, yes, it did work first time. Yeah, and it was absolutely marvellous. You know, how many of your desktop computers could you leave switched off for 2 years and then switch it on. But I've been told since that it actually didn't work first time. They did have to switch it on and off 3 times. But I haven't heard that they had to take the plug out or check the fuse. Okay, so, but it woke up, when was that? January, that should be. January, somewhere it woke up. And then between January and August, it was accelerating and getting closer and closer to the comet. So let's take a bit of an aside here and do some cultural stuff and ask why it was called Rosetta. So the Rosetta Stone, after which it is named, is in the British Museum. I don't know if many of you have seen it. It's about this sort of big, and it's one of the cultural things in the British Museum, along with the Elgin marbles, and its ownership is probably just as secure as the Elgin marbles. It's got on it a decree on behalf of King Ptolemy V from 200 years BCE, and it was dug up from the Nile Valley in 1799. And at that time, people couldn't interpret hieroglyphics. They knew that the ancient Egyptians drew in these little pictures, these cartouches, but they couldn't interpret them. On this stone, though, it's got the same decree written in hieroglyphics, Demotic script, and Greek. Demotic script was the script, the languages that scribes used to show proclamations and things like that. And so because you've got these 3 things, and people could read this and see it said the same as the Greek, the assumption was the hieroglyphics said the same. So it allowed, for the first time, translation of hieroglyphics. And that was important because it gave us a much better understanding of Egyptian culture, which is very important because that's the cradle of civilization, where trade and culture and picture making and music and all those sort of things were thought to have really got going. And so by understanding now hieroglyphics and Egyptian culture, our eyes were opened to the dawn of humanity and social behaviour, if you like. So when you want to name a space mission, which is going to open our eyes to the dawn of the whole of the solar system and understanding where life has come from, then obviously you're going to go for something like Rosetta. The decree, actually, by King Ptolemy, it says, if you worship me as a god, I will let you keep all your land, which is, fair exchange, really. So that's why it's called the Rosetta mission. Now, why Philae? Philae is the lander which sits on Rosetta. And Philae is an island down here in the Nile. And on the island of Philae is a huge temple to Isis, the mother of all the Egyptian gods. And this is a real cultural heritage thing. It's a UNESCO site of cultural whatnots. At the gate, at the entrance of the temple, were 2 obelisks. And on the obelisk were cartouches again and Demotic script, Greek. And again, the obelisks from Philae helped to interpret the hieroglyphics on the Rosetta Stone, so helped to understand the Egyptian language. And so in the way that the obelisk at Philae illuminated the wording on the Rosetta Stone, the instruments on the Philae lander are going to illuminate the results that we've got from the Rosetta orbiting spacecraft. It's all very logical. The obelisk is in the grounds now of Kingston Lacey, which is a National Trust property down in Dorset. Okay, so that's why Rosetta and why Philae. So we've got all the way to July. Now, the first images, the first pixelated image, or the first image of 1 pixel, showed the comet was, you know, approximately pixel shaped, and then we got one that was 5 pixels and it was approximately 5 pixel shaped. And you know, people were doing landing site selection workshops on 1 pixel, and then you know they really refined them when they had 5 pixels, which is pretty amazing. Pretty much of a waste of time, I would think, as well. So but the understanding was that this was approximately comet shaped, where approximately comet shaped is, you know, something like a potato, right? You know, it's definitely not spherical, but you know, it's sort of a single lobe. And in July, this was the first decent image we got of the comet. Now, if you can imagine that yellow with a little red beak and an eye, it looks very much like the plastic ducks that you sail in your bath, okay? And so when scientists saw this, you know, the immediate reaction was, oh, duck. You know, that's absolutely what they all said. Because what it meant was all the shape models that they had constructed were wrong. Now that's important because we needed to know the mass of this object. You're going to land something on it, you need to know the gravitational attraction between the two objects. This is only about 5 miles across, so its gravitational attraction isn't going to be very big. So you at least, you know, need a first order approximation as to what it is. And so you make an assumption about the density, you've got to know the volume. To get the volume, you've got to have a shape model. If suddenly your thing that you're modelling has 2 lobes, which may or may not be made of the same material, and you have no idea what's holding them together, then it really makes your mass calculations very, very difficult. So there was...
I think they realize it's blue tack.
Sorry?
They now know
it's blue tack. Yeah. It is, but it's a very, very special type of blue tack. You know, it's it's got...
It wasn't known.
Yeah. So as we, you know, there was discussions, you know, like, shall we stop the whole mission? It's like, you know, because we can't work out the mass. It's like, no, it's been going on for long enough, you know, give it a whirl. So then we got closer, September 2014, and it wasn't just that it was duck-shaped. It was duck-shaped with just the most amazing landscapes. And this was totally not expected. You know, we've never had anything as close up and as detailed a view of a comet as this. And you're starting seeing this amazing morphologies, the amazing landscapes, the crevasses, sort of mountain valleys, U-shaped valleys. You can describe them all in terms of the geology or the geography of the Earth or of the terrestrial planets, but we don't expect to have things like that on a comet. This was an image taken about the same time, maybe a month or so earlier, by the VLT, or from the VLT. And that's a much more traditional sort of picture of what a comet looks like. And so when you're up close, you don't actually realise that, yes, the tail is there. Yes, there is a lot of degassing going on. You've got the dust, you've got the plasma, you know, it's all happening. But when you look from the Earth, it's all there. So again, there was another hiatus of, you know, are we going to be able to land on this? And so you know, more working groups were set up to actually decide where the landing site was going to be. 10 sites were selected. It was come down to landing site J, and there was a competition to name the landing site. And it was named Agilkea. And there was a competition so people could suggest the names. And so actually I suggested the name Agilkea. So along with quite a lot of other people. All right, not just me. But I got my certificate. Now, Agilkea was an absolutely obvious name. So keeping the Egyptian theme, coming back to where Philae is, this island. So the Temple of Isis was built by the ancient Egyptians. Here, just a little bit to the north of Philae, is the Aswan Dam, which was built by modern Egyptians. And what the modern Egyptians hadn't sort of taken into account was that when they put this great big dam or series of dams there, it was going to change the water level in ways that hadn't totally been predicted. And the island of Philae was flooding on a regular basis, and it was eroding away this great cultural monument. And so UNESCO moved the Temple of Philae stone by stone and completely rebuilt it on the island of Agilkia, which is just a little bit further north of Philae, which doesn't flood. So Agilkia became a safe haven for the Philae lander. No, Agilkia became a safe haven for the Philae temple, and so we were hoping that by selecting the name Agilkia for the landing site for Philae, it would be a safe haven for Philae. Of course, things don't always go to plan, but never mind. That was the reasoning. So bringing you sort of up to the day of the landing, and this is where things got, really, really exciting, because we'd had this last picture of Philae taken by the navigation cameras on Rosetta. That was at 10 o'clock Central European time, 9 o'clock GMT, UT. So that was it. It's gone. Now we have to wait 7 hours. Now, when NASA delivered Curiosity onto the surface of Mars, they did this 7 seconds of terror video. Well, we don't do things by halves in ESA. What 7 seconds? No, let's go for 7 hours of nerve-wrenching tension when you're waiting and waiting and waiting. And so Philae was released, and then immediately rumours. Its thruster isn't working. They nearly didn't release it. It wasn't sure that all systems were go, but it's like, but they did it. All systems were go. People were in Darmstadt. I was in Darmstadt, which is where mission control. Oh no, there's two places. There's mission control and mission operations, and I could never remember which one I was in. All right, I was in Darmstadt. Let's call that mission control. And in Cologne, 100 miles or so away, was mission operations. So in Darmstadt were, the great and famous, the ministers of science, Angela Merkel's special envoy, loads and loads of science journalists, the principal investigators of all the instruments on Philae. So Ian Wright was there. Ian Wright is the PI of Ptolemy. He's also my husband. And I was there because I'm a scientific advisor to the Ptolemy team. I'd been invited in my own right. And so all these people were there, all these journalists, and at the Science Operations Centre were the rest of the teams. So the other 5 guys in the Ptolemy team were down in Cologne. And so Ian was in constant communications with them, but it was like, yeah, nothing's happening. Yeah, nothing's happening. Yeah, we've still got 5 hours to go. Yeah, nothing's happening. And so in order to keep all these restless people engaged for 7 hours, ESA showed the film Ambition several times, to get you all stirred up with the music. There was loads of food and loads of drink. And, occasionally somebody had come and give a little talk about something or other. But the journalists, they were interviewing anybody who stood still for more than about 20 seconds. They'd have, a microphone thrust up their nose to talk about it. Do you think it's going to be successful? It's like, yes, I think it's going to be a great success. No, I think it's going to be tragic. What can you say? So this goes on all day, and it's just winding up the tension. And journalists, by and large, don't understand planetary or orbital dynamics. So they were told that Philae would land the signal would come back from Philae at 17:03. That because of the 20-minute travel time, that means that Philae actually landed at 4:45. Did I say 3? 3? What did I say? 3 minutes past 5. 4:45 was when Philae actually landed. And not to expect anything before 5 o'clock. Nothing would happen before 5 o'clock. From about 4 o'clock onwards, journalists were saying, well, why hasn't anything happened yet? Why hasn't it landed yet? And he said, because it's not 3 minutes past 5. You know, oh, yeah, but shouldn't something have happened? No, nothing's going to happen. You know, if engineers say it's going to happen at 3 minutes past 5, it's going to happen at 3 minutes past 5 because they know these things. They understand how gravity works and how orbits work. No, it's not gone wrong because we haven't heard anything and it's now 25 past 4. So it just kept going and going and going. And so from about 4:30 onwards, the great and famous gathered at the front of this lecture theatre where behind us there was this big picture of mission operations with, you know, the banks of computers and people looking and things like this. And it was just getting more and more and more tense. And so I'm giving that as we were shown this, yeah, at 4 o'clock. It's like, oh yes, there is something. You can see we are getting close. It's like, great. Feli's camera is actually working and it's taken a photograph and you can see its leg. And that kept us going for a bit longer. But like I say, the tension was amazing. And that's the excuse that I give for my completely and utterly over the top response, because what you've got to remember is that this wasn't just 10 years since orbit. This was a whole lot longer. We had to deliver the instrument in 2001 in preparation for the launch. Now, the launch should have been in 2003. We had to deliver in 2001 because our instrument was the first, you know, it was the deepest in, and everything else was going to be assembled around it. Comet Churyumov-Gerasimenko wasn't the comet we were supposed to go to. We were supposed to go to Comet Virtanen. But the year before, the launch prior to the Rosetta launch, the Ariane spacecraft, there'd been a malfunction. And so they put the whole of the Ariane program on hold while they investigated what had gone on. And so that meant that all those careful orbital dynamics that had been calculated for Comet Virtanen had to be redone very, very quickly to find that there was a comet which had the right sort of, you know, it was in the plane of the ecliptic, so we couldn't, you know, we didn't have to have too much more of a delta V to get there. So that was 2001, but prior to 2001, we were building the thing. Now, we had to get the instrument selected, we had to get the mission selected, we had to get the money from, well, whoever it was, P-Park, Science Engineering, I can't remember what the name of the research council was, possibly P-Park. You know, all these, you know, I'd say you had to get your ducks in a row, but, you know, that doesn't seem too appropriate. But I've got a fax dated 1995 from Colin Pillinger, who was one of the chief proposers of the mission, which said, right, we've got the go-ahead from ESA, now all we've got to do is get the money, all right? And so that was 1995. And so up until then, you know, before that, there was work behind the scenes. And Derek, you must have been very much involved in it, were you, in some of the proposals? No? Not at all. Okay, go on.
Could you please briefly explain how the landing happened in terms of the physics? I mean, was there a little booster that pushed the lander, or was it mostly gravitational?
Yes. What was supposed to happen...
And then did they deploy a parachute?
No, no parachutes. Why would you have a parachute?
I was joking, please.
I just wanted to check that you were joking. So, so, you know, coming up to all this, it was just a major release of tension. Ian wasn't in the room. All the PIs had been taken away, you know, so they could talk to their teams in this operations centre. And about 10 minutes after this joyous, you know, hey, it's landed, fantastic, we've got the signal, Ian came back and I gave him a big hug and took a selfie of the two of us smiling. I said, you must be so happy, you know, because you've worked so much for your scientific career on this. He said, in my ear, he said, it's all gone tits up, keep smiling. And so it's like, right, okay, what's happened? And all the science teams knew it had bounced, because they were, you know, they'd get the signal and they could see it wasn't in contact with the ground. What should have happened was there was a thruster on top which was going to push and keep the lander pushed down. It had 2 harpoons that were supposed to fire and anchor the landing craft. And then on each of the legs there were sort of spikes, crampons sort of thing, which would sit on the surface and hold it on the surface so it wouldn't go. All those things didn't work. So that we knew, that was the worry at 10 o'clock in the morning, that the thruster wasn't working. That was already known, that there's something wrong with that. But there was an assumption that the harpoons would fire and embed themselves. And it looks as if they didn't fire, and we don't know why. So Philae landed and then bounced again and again, 3, 4, maybe 5 times before it came to rest.
These harpoons, wasn't there the danger to sort of catapult it back?
There was, but it was all supposed to have been very carefully calibrated and calculated, all right? You know, we have to trust the engineers knew what they were doing because they were German, right? And so Philae, instead of...
All is clear, you can go on.
So in Philae, instead of landing like that, in the middle of this sunlit plain, landed like that, up against either the edge of a cliff or perhaps wedged in a crevasse. And so for 60 hours, Philae worked because it had a permanent battery. And for 60 hours, we got an amazing amount of data. And then the battery started to die. And the hope was that, the plan had been that the solar panels on Philae would charge up a secondary battery because the main battery wasn't rechargeable. So we got a huge amount of data. We got about 80% of the experiments we wanted to do. We got all that done before the battery died. And if you followed poor old Philae on Twitter, you know, I'm getting very tired now. It was really, really moving, you know, even though I knew who was doing the tweets, you know, it was like really, really moving. This image was released the next day, which was of Philae as the orbiter went round. And you could see, here it is, remember, this is UT now, not Central European time. So at 3:15, we could see 3:20, and then here it is again. And then at 18 minutes past, that was the previous orbit, nothing there. At 15:43, touchdown, they reckon those 3 are where it touched down. So 15:43, all right, UT, 16:43 Central European time, absolutely dead on time for the 20-minute signal to come back at 5:02. So absolutely marvellous, but unfortunately, it's not there. So they think it bounced a few times and it's possibly here. Now, there were last week released some images where they thought they might have found Philae, and we'll learn a bit more about that in the coming weeks, I suspect. So just to talk about Ptolemy, the instrument that I'm associated with, okay, what is it? It's an instrument that can sniff and can taste. So the sniff mode is just gas, and any dust that's entrained in the gas goes into the detectors, which are a combination of a gas chromatography system and a mass spectrometry system. And the other part is where a solid sample goes into an oven and then gets heated up and combusted into carbon dioxide and water. Now, unfortunately, this didn't work because the drill wasn't working, so we'd got no way of getting the gas and dust into the oven. So what were we doing was we got loads of results, some really good results, which I'm not going to tell you about because they're under embargo. I'll just say a little bit more about Ptolemy. This is the prototype, and that's Sasha, and he's 6 foot, and he's standing up. And you can see it's big, it's huge, it's cast iron, welded together, a huge amount of electricity, God knows 32 amps or something required to power all these valves, lots of compressed air. So this is the lab prototype. We brought it down to something a bit more compatible with being launched on a rocket. And so this is Ptolemy. And so this is all the gubbins. These two big tanks here have got helium in, which are the carrier gas for getting the dust into the system. And so now this weighs, I can't remember how many kilograms, but it's a few kilograms. And so, yeah, no, that was pretty good. That was done with Rutherford Appleton. All right, now some more general. Here's a general picture of some of the marvellous landscape. Here's another general picture of the comet taken a few weeks ago, showing a jet. They call this the farting comet, which is a bit amazing. So you can see new jets are coming and going all the time. So some of the results that we've had, again, I'm saying we, I'm not an author on any of these papers, were published. The data have come back from the Rosetta instruments on the Rosetta spacecraft, and they were published in Science, here we go, at the beginning of the year. And here's the spectral reflectance data. And it's not actually reflecting very much. It's black. The comet's black. It's blacker than the blackest black thing that you can ever think about. And it's got an albedo of approximately 0, just a little bit more than 0. And this is really, really, really showing that the model of a comet of being ice with a rocky nucleus, that's long since gone. The model of a comet of ice and dust all mixed up together is also not so secure. Okay, a lot of the ice is subliming away as the comet gets closer to the sun, but you would expect there still to be some ice there. I mean, the temperature on the surface is pretty damn cold. So, but there seems to be hardly any ice there at all, which is really interesting. However, there is water, and these again are data from the same issue of Science from an instrument that's on the orbiter. And here are the Rosetta data. And here are data for, this is the deuterium-hydrogen ratio. Here's our protosolar nebula as indicated by the gas giants and the Sun, and the Earth, Enceladus, other comets, and here is Comet 67P. Now, the idea of this, partly of the mission, is to see, if you're mixing together protosolar nebula with stuff from comets to make the Earth. And it's like, okay, well, yeah, maybe we could, but we're not enormously certain. So there's been some worries about how to interpret this data. Now, the COSAC instrument, is it the COSAC instrument? No, it's not COSAC. My mind's gone a blank for a minute. The instrument that runs this has got lots and lots more data. And these were the first data from the material that was degassing as the comet's tail was growing. So we're going to be seeing publication, I hope, in sometime later this year, I'm not sure when, of how this has changed as the comet gets closer to the sun. These are Ian's results, or the Ptolemy team's results, which he presented at the Lunar Planetary Science Conference in March when everything was still under embargo. I put this up here for the benefit of all you astronomers, astrophysicists, and especially the cosmologists. We recorded a demonstrable signal that is far in excess of any background, unlike Biceps 2, I am tempted to say. So we did get a lot of signal, which is pretty good. And those molecules are mainly carbon bridged by oxygen atoms, not with, we don't think there's any nitrogen there that we can see, which is very disappointing in some senses, because one of the things we wanted to look for were the building blocks that went to make nuclear bases, amino acids, and so on and so forth. But we're still working on the interpretation of the data. So what's next? The Rosetta mission continues. Our closest approach is August 2015. Rosetta, as of last Friday, was about 250 kilometres above the comet's surface. And if I'd been giving you this talk last week, you'd have got felines taking a short break and we're listening out for a signal. But of course, you know, I've had to revise the talk, heavens. So a signal was sent on the 13th of June, which is fantastic. We had an 85-second signal, and then there's been two 10-second signals, and there've been no signals since then. But Rosetta has been moving. And so the problem with bringing Rosetta closer to the comet nucleus is that there is so much dust and gas coming from the surface of the comet. Now, Rosetta has to navigate by the stars. It's got a star tracker, and the additional dust coming from the comet can knock the star tracker out, and it has done on at least 2 occasions. And that, sends Rosetta into a bit of a tailspin, and it doesn't like it too much. So there is a real concern. And so there is now even more tension between the Philae PIs and the Rosetta PIs, because the Philae PIs say, well, come closer, come closer, come closer. We want to do some concert radio. The radio instrument needs to be closer to get a better idea of what's going on in the internal part of the comet. But the PIs on Rosetta obviously need to stay further away, because they can't, otherwise they're in danger of losing, well, we'll lose the whole thing anyway. All right, so that's where we are. We're getting on, we're interpreting and understanding results, and we're waiting now. The Rosetta, it's confirmed it's going to come down to 180 kilometres, and it's doing the manoeuvres to get it down to 180 kilometres, and then it will be assessed. It should pick up the signal from Philae twice in every cycle as the solar power, gets better. Now, what I've got a cartoon here, which...
Over 10 years had passed since Rosetta and Philae launched on their exciting mission to Comet 67P Churyumov-Gerasimenko. After 3 months investigating the comet from orbit, it was time to send Philae to its surface. A long night of final preparations lay ahead of them. Finally, the moment everyone had been waiting for arrived. As the world held its breath, Rosetta moved into the exact position needed to make sure Philae would reach the landing site that scientists on Earth had picked earlier in the mission. Philae and Rosetta were sad to be going their separate ways, but excited at the same time, because this is what they had been waiting to do. Philae was away. It would take 7 hours to reach the surface, but Philae wanted to get started on his measurements right away. He could soon see the surface in incredible detail, and the moment he had been dreaming of had finally arrived. He had reached the surface of the comet. But all was not right. His harpoons did not fire. Philae realized he couldn't relax yet. He was rising from the surface again. Philae was scared he might drift off the comet completely. This was not in the plan. But eventually, he came back down again. However, as he looked around, he realized he had landed in a completely unexpected location. Philae immediately set to work on studying his new home. It took him just over 2 days to conduct all the experiments he had brought with him. After all his hard work, Philae began to feel tired, so he made sure to send all the data he had collected back to Rosetta. As the sun set over Philae's new home, he fell into a deep sleep, safe in the knowledge that he did his main job well and that his family of comet-chasing heroes would be proud of his achievement. Who knows? Perhaps one day enough sunlight would fall on his new landing site and wake him up so that he could carry on investigating this incredible world. And so, as the comet moved over closer to the sun, Rosetta prepared for the next part of her exciting adventure.
Philae woke up on Saturday the 13th of June and I put on here, I need a new t-shirt, all right, because that bit isn't on the back of this one. So we're waiting and we're still waiting, and I hope that our wait won't be in vain. There will be housekeeping data for the first week or so. It's not anticipated that there will be any science operations over the next week. As Philae warms up, it's pulling powers of about 25 watts. It needs about 25 to 30 watts to get things going. It's got a lot of data already on board which have to be sent back and interpreted, and that's what's going on at the moment. So it's like really exciting. So watch this space. Thank you very much.
Some questions.
Are there any options for using the drill that I gather first attempt shot out and came back empty?
Well, the problem is the drill. You know, it's underneath Philae, and if Philae's on its side, then the drill is drilling into thin air, literally. Well, the Philae solar panels are all around it. It hasn't got wings like this. And the solar panels can rotate. And it's thought that the momentum of... Well, first of all, we don't know if Philae is still in the same position, because if ice is sublimed away, we don't know what's happened underneath Philae, the side of Philae. That's why they're desperately waiting for photographs. There has been some thought that it's more or less as it was, and if it is as it was, there's nothing that can sort of tip it, flip it onto its side, onto its feet. The solar panels can rotate, and there is a wonder that if you did something with the drill, something might happen, But it's like, I'm thinking, well, if you're drilling that way into nothing, there will be some reaction just from the motor of the drill, but I don't know whether it's going to my way of thinking, that's not going to tip something like that, But then again, I'm not an engineer, so how can I say? So it's very imponderable, all right? They're not planning on basing much around getting drill cores. But Ian reckons that their ovens are going to be full of dust which has accumulated there during the last 7 months. So he's very hopeful that they'll have volatiles and other dust, even if not ice, which would be good. Question up at the back.
What specific considerations were made to choose the landing sites and then finally settle upon?
It's a trade-off. It's got to be as flat as it can be, so level. It's not got to have very many boulders on it. But the biggest trade-off is in the sunlight, because it's got to have enough sunlight to keep the solar batteries charged, but too much sunlight in the full glare of the sun, the electronics would fry. So it's got to be, sunny but not too sunny sort of thing. Yep.
One of the photographs you showed, which is the sort of gorge
There appears to be rock there with strata.
Yeah, I really rushed past this because I glanced at my watch and thought, oh crikey, I'm a bit behind time. Yeah. This is one of my favourite photos. And you look at this and you think that could be stratigraphy on Earth. Yeah. You look at that and you think, well, I've got either some bedded sediments here, you know, or different even basaltic layers. I've got a U-shaped valley which has been carved by the motion of a glacier, and I've got wind-blown dust. All right. Well, we don't have glaciers carving U-shaped valleys. There's no wind-blown dust, and certainly nothing to make bedded sediments. So to try and interpret these landforms in you know, by analogy with terrestrial things is not right. The dust is really interesting because it does coat everything, and it's sort of assumed that it's from when the jets, when a new jet opens up. And material is pushed off the surface of the comet. Some of it, you know, most of it goes into the tail and is lost, but some of it does fall back. Actually, some of the larger boulders, I mean, obviously you've got shadows here, but in some of the larger boulders, you've got what looks like some form of aerodynamic drag. So you've got particle sorting as these grains fall back. But what these are, I have no idea.
You've got geologists looking at that.
Oh yes, yeah. Any other questions? Yeah.
So I didn't understand one thing. Is it awake now or not?
Yes, Philae's awake. Philae, they know Philae is awake, but it's making sure that there is a constant link. They'll be able to link twice in every orbiting cycle. And what they're hoping for is that they make that link constant. At the moment, the longest link has been 85 seconds because then Rosetta has moved out of range, or it's moved away, it's moved below the horizon. So they're now calculating what the longest time they can keep the two. So it's not in any sort of geostationary orbit or anything like that, and it can't.
And in case you will be able to collect some new data now that the comet is closer to the sun, can you make some signs similar to the
Oh yes,
previous
yeah,
data, or
yeah.
Or the
Yeah, the main reason for the communication is to transmit data back or commands forward. And so there are packages. People have been working for the last 7 months on how are we going to, what order are we going to do things in, how are we going to upload new commands. And so they've been working on these new command sequences all the time, weekly teleconferences of this, that and the other. And so the command sequences for the instruments on Philae, they're all ready, they're all set, they're ready and waiting to go. And the command sequences will be, first of all, get as much data back as is already stored in the memory, then send up the first tranche of science experiments, which will be ones that only need a low power, and then gradually medium power, high power. And of course, Ian's experiment, Ptolemy, is high power because it's got these ovens which need to be heated up. So we should be able to do some sniffing in the second tranche of experiments, but any tasting won't be until the final tranche.
Monica, this is a question of some desperation.
Okay.
Are the spectroscopic results of either Philae or Rosetta up to trying to detect the diffuse interstellar bands? George Herbig and I have tried with comet tails.
Yeah.
But the diffuse interstellar bands don't like heat. And we drew a blank, both with comet Hale-Bopp and with halibut.
I don't know. I don't know the answer to that question, but I can attempt to find out for you.
Well, that would be,
Yeah.
very grateful.
Yeah. I'll find it. I'll try and find out.
Very happy before I pass on.
Okay. I'll see what I can do. Any other questions?
I have
No.
a question
Well, we're hoping so, yeah, because it's got, I can't remember whether it's 6 or 7 cameras on board Philae. And so we're hoping that there are images in the data packets. But I asked Matt Taylor this morning, any images yet? And he just emailed me back and said, nope. So not yet, but we're hoping.
You said there were some results under embargo. Do you know when we might hear them?
Oh, well, they're in Press in Science. So, you know, it's a month or so, I think. Yeah.
After that 100% of project completion, what are the plans for?
Right, well, Philae is still going to be sitting there, okay, and assuming its solar panels keep working, then Philae can just keep going, all right, but, and the comet comes around every sort of 6 years or so, so you can imagine, you know, in 6 years' time, Philae's like, oh, hello, it's me again, you know, let's start measuring something. However, Rosetta won't be there to transmit data or to do anything because Rosetta has big solar panels, but they will become very, very degraded because of being so close to the cometary tail. And also it has fuel on board as well for the orbital maneuvers, but only a limited amount of that. So the idea is that when Rosetta gets to its end, there will be a controlled descent onto the comet's surface, not to where Philae is, but to somewhere else, so that we can look at a different place. That's the plans. Mission end is nominally December this year, but there is a hope that they will be able to keep it going for another year after that. So as we come through perihelion, we watch the tail decay.
So Philae can't communicate with us directly?
No, it has to go via Rosetta.
It will shut down in a year when it gets away from the sun again?
Yes.
Wake up in 6 years' time and Rosetta won't be there.
Exactly, yeah. So I mean, if Philae hadn't woken up this time, you know, I could imagine it, you know, in 6 years' time or 12 years' time or 18 years' time, when so much ice had sublimed away that the crevasse was, you know, it was now a level playing field or whatever. It was just like, you could imagine poor old Philae saying, hello, I'm here. And there's like nobody to talk to. I mean, it's just absolutely heartbreaking. But, but that didn't happen, so he's talking.
About that?
Sorry, say again?
Will there be a cartoon about that?
I'm sure there'll be much more of a cartoon, yeah. I think there are 4 or 5 of these cartoons on the Rosetta site, and they're absolutely brilliant. I think they're really great resource.